This is tutorial question Q1a. We're asked to determine the period of this discrete time sequence x1n. We know that for cosine, theta plus 2 pi is equals to cosine theta. And in fact, it is not only 2 pi. Any integer multiples of 2 pi, the terms on the left is equals to the term on the right. So cosines are 2 pi k. How do we apply this into this equation over here? This is a cosine pi over 6n plus a phase shift. What we need is that in this particular case, once we have n sample, capital N sample separating the sequence, we want it to be periodic. So therefore, this n sample must play the role of the 2 pi k. And if n can be associated with 2 pi k, then the left and right sequence would be the same periodic. So what do we do? Well, we can actually ignore the phase shift term over here because both axes on the left and right hand side. So we are now interested only in this small n plus capital N terms, and that these capital N terms must be equivalent to 2 pi k, where k can be 1, 2, or 3. Now, when we solve for k equals to 1, it means that we are only thinking of it to be one period away. So let's expand out this term, pi over 6n plus capital N on the left hand side, and pi over 6n plus 2 pi on the right hand side. If these are equivalent, then we can solve for capital N. In this particular example, we find that capital N is equals to 12. If we have used k equals to 2, and when we solve for it, then we get capital N equals to 24. But we prefer the smallest period because that is the fundamental period. So this is the answer. Now, we can view this problem in another way. We can generate the complex exponential e j 2 pi over 12n. This of course is equals to ej pi over 6n. And what is ej pi over 6n? It is a complex number cosine pi over 6n plus j sine pi over 6n. This is by Euler's equation. It has a real part and the imaginary part. And the thing that is changing is n. And as n changes, then what we'll get is a rotating phasor, which is exactly this diagram over here. You can actually see that when n equals to 0, cosine 0 is 1 plus j sine 0 is sine of 0 is 0, so it's j0. So this is the first example that we get is 1 plus j0. So this point over here is the first sample. Then as we increase n, this will be the second sample. And as we increase n again, this will be the third sample and the fourth sample and so on. And this is a rotating phasor because along this axis over here, this is time. Time in the discrete sample space. So its time is n. Now, what you'll see is that it's a rotating phasor that is moving anti-clockwise if you just substitute different n to it. You can also view this 3D-dimensional rotating phasor from the point of view of here. That means you put your eye here and you're looking into a time that is coming out. So you are seeing this plane, the horizontal plane of the real axis and the vertical plane as a surface. And then in here you will see that this is the first sample over here. This is a second sample, third sample, fourth sample, and again you will see the idea that this is a phaser that is rotating anti-clockwise. Notice that the point is constant to the origin because it is 1 exponential j pi over 6 and 1 doesn't change. So this is actually the radius 1 over here. Finally, remember that we can also view this as two separate diagrams, one for the real and one for the imaginary. So this is the third diagram that you can see. This is the real part of e j pi over 6n, and this is the imaginary part. And this is, of course, looks like the cosine to you, and this looks like the sine to you, and here is n moving from time 0 to time 20 and 25 and above. Now, maybe you should now ask yourself, what in the world is this value pi over 6 doing here? How do we see it from the figure? Well, you can see it most clearly from this diagram. You notice that as the sequence goes up by each step, this angle is pi over 6. What is pi over 6? Is equals to 180 degrees. Divided by 6 is pi is 180 degrees, and therefore this is 30 degrees. So you'll see that it moves by 30 degrees each time. This is one way to see it. The other way, of course, to see it is here. Each sample is 30 degrees. So in the cosine, when you move by 3 sample, 1 sample, 2 sample, 3 sample, you reach 90 degrees. Okay, so with that, we can see that in this question, we can find out quickly what is the period n equals to 12. And how do we interpret n equals to 12? You can see that the sequence repeats after 12 samples. This is one way. The other way is in the real, it repeats after 12 samples. So is the imaginary. Thank you.